Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about predicting the change in entropy. Okay, so before we start talking about making predictions, maybe we should talk about what entropy is. Okay, so entropy has the symbol S, and it's a measure of the disorder or randomness in a system. Okay, so it's a measure of disorder. And the reason why we like to talk about disorder is because the universe tends to want to become more disordered, right? Think about your bedroom. You go into it, you clean it all up, and if you just kind of live out of your room for the next couple of weeks, it's just going to gradually become less and less organized as time goes on. Or perhaps think about laundry coming out of a dryer. If you were to pull the laundry out of your dryer, what's the chances that when you pull it out, it's all going to be sorted and folded for you? Pretty low, right? There's not going to be that amount of organization. When your clothes comes out of the dryer, it is going to be disorganized and random. So because the universe really tends towards more randomness and more disorder, as scientists, we like to measure it. So that's where we get entropy. And the thing that we want to talk about more than just entropy itself is changes in entropy. Did it become more disordered or did it become less disordered? Okay, so an entropy change is a change in the amount of disorder or randomness in the system. So if we can predict that a system is going to become more disordered, that the entropy change is going to go up, right? We're going to have more entropy, more disorder, so the change will be positive. Then it's more likely that that chemical reaction or process is going to be spontaneous, that it will just naturally happen. Okay, so the rules for this. If you're going to predict some entropy changes, increasing the temperature of a substance always increases the entropy, always. So when you heat a substance up and you increase its temperature, what you're really doing is causing the particles that make up the substance to move faster. So let's say they're moving pretty slow, you add heat to it, and now they start moving faster. So adding heat increases the amount of kinetic energy. And if you have done anything, okay, let's say you play video games, you look after little kids, right, you babysit. Anytime the things are moving slowly, there's more order to that. It's easier to keep track of what's happening, right? Picture it here. You've got a cold object, and all of the little particles are moving pretty slowly. That's why there's like very short little lines behind them showing that they're moving slowly. So if this is little kids that you're looking after, you're babysitting, if they're all moving relatively slowly, there's a certain amount of order to that because you can keep track of them all. You know what every single one is. But if you consider a hot object, okay, you still have your little particles and you see all the little lines are much longer now. This would be like if you have the same group of little kids, but instead of just kind of playing quietly and moving around slowly, they have just gotten up from their naps, they're all energized, and so they're running around the room. Okay, there's a lot more randomness or chaos to that because if the little kids are running, it's harder to keep track of them. It's harder to see what they're doing. So when you heat an object, the particles go from moving slowly to moving quickly. And if anything is moving faster, then that increases the amount of randomness or chaos that there is, which means that your entropy is going to be higher. So you go from low entropy at low temperature to higher entropy at higher temperature. So if the amount of entropy is going to go up, that means the change in entropy is positive. Okay, let's talk about a second. If you take a substance and you dissolve it, then the entropy automatically goes up as well. Okay, let's think about sodium chloride in water. Okay, so you've decided that you're going to take some salt and you're going to dissolve it in water. When you have the two of them separate, there is some order to that, right? If you have some salt in your hand, then everything in that pile is salt, sodium chlorides. So you've got sodium chloride, sodium chloride, sodium chloride, very organized. If you have the glass of water that you're going to dissolve it in, again, it's pure water. So it is pretty organized, right? When you put them together and you end up with salt water, the sodium chloride dissolves. Now what you've got is more of a mixture, right? There's a water, and then next to it there's a sodium, then there's more water, then there's a chloride, then there's more water, then there's a sodium, right? There's more randomness to it. So when you take a substance and you dissolve it, you are going to increase the amount of disorder. Increasing the amount of disorder increases the amount of entropy. So undissolved, low entropy, dissolved, higher entropy, and if your amount of entropy is going to go up, that's a positive change. You can almost think of it like if you have coins. Let's say that you have quarters and you have nickels. If you have only one type of quarter or one type of coin in this hand, that's got some order to it because it's only one type of coin. If you have a different type of coin in the other hand, again, that's pretty organized because there's only one type of coin. But if you mix them together and shake them up, now you've got a mixture of, say, quarters and nickels or quarters and dimes or whatever coins you have. And as a mixture, it's a lot more disorganized. Okay? And so you can see that here in my examples. If you are going to go from calcium oxide solid and turn it into calcium oxide aqueous. Okay, now the way we write this in chemistry, we just go from the solid to the aqueous. And the assumption is, how do you turn something from a solid into an aqueous? Well, you're going to add some water. So you're adding water. But the water is not the most important thing here, so we don't actually write it. It just kind of gets implied into the question, right? So you're going to go from calcium oxide solid to calcium oxide aqueous. Over here on this side, this would be like your calciums, all one pure substance. This would be like your water, all one pure substance. And the minute you put them together and they become aqueous, you get this. You get a mixture. So there's calciums, there's oxides, and there's waters all floating around together. Now let's say, though, that we want to talk about something a bit more difficult. Let's say that you have a double replacement reaction. So you have aqueous sodium chloride reacting with lead nitrate to turn into sodium nitrate and lead 2 chloride. Okay, so it's a double replacement. The sodiums and the leads switch places. In this problem here, the sodium chloride is already aqueous. So it's already in a container where you have a mixture of the sodium chlorides. Okay, there's my sodium chlorides. And your water molecules. So here's my water molecules. So this one here is already disorganized because it's already aqueous. When you talk about your lead 2 nitrate, same deal. You've got your container, and this stuff is already dissolved. So you've got your lead 2 nitrates, they're here in my container. And it's aqueous, so you do have water molecules as well. So they are dissolved in water. So for both of these two chemicals at the beginning, you do have quite a high amount of randomness, quite a high amount of entropy. So high entropy, high disorder, high entropy, high disorder. And then what do? The sodium and the lead switch places, and you end up with sodium nitrate. Okay, well this sodium nitrate is also aqueous. So you are going to, again, have sodium nitrates in the container, and it's dissolved, so you'll also have some waters in the container. So again, this is nice and random. So you started with two things that were quite disorganized, and you still have something that's quite disorganized. But if you look at the last chemical here in my chemical reaction, the lead 2 chloride is a solid. It's not aqueous. Okay, that's a little bit different. So for this one here, all of your lead 2 chlorides, they're solids. So they're all down here in the bottom of your container, right? When you make a solid, it starts out floating in the water, but then over time it settles to the bottom. So this would be my pile of lead 2 chlorides. The water is floating around here on top. Now you can see that what I've got here is very similar to the original situation up here. I've got the two different things separated, right? All of the lead 2 chloride's on the bottom and all of the water is on top of it. This has a very low amount of disorganization. This has a very low entropy. So low entropy. So I went from high entropy plus high entropy, high amounts of disorder, to having a high entropy, right? This one has a high amount of entropy, plus something that has a low entropy. So if I look at this entire chemical reaction, I can see that in the beginning, I had lots of disorder. I had lots and lots of entropy. But at the end, I have less entropy, right? One of my products is a solid. It's separated out from the water. It has increased its order. It has decreased its disorder. So I have low entropy. So for this one here, I would have a loss of entropy for the entire reaction. And if you got a loss of entropy, your entropy is going to drop. So my delta S here, my change in entropy, is going to be negative because there is a loss of entropy. Okay? So when you're doing a chemical reaction, often you do have to think about each of the reactants and each of the products and decide how much disorder does each one have, and then as a group, how much disorder is in the reactants versus how much disorder is in the products. And then you can decide if it's going to go up or if it's going to go down. All right, let's move on to the third one. If you talk about solids, liquids, and gases, solids have the least amount of disorder, so the least amount of entropy. Liquids have more disorder, so they have more entropy. And gases have a huge amount of entropy, and therefore huge amount of disorder. Okay, now if you've studied solid, liquids, and gases in one of your science classes, right, they probably cover that quite early in the science curriculum, then you know that a solid is very ordered, right? They line themselves up perfectly next to each other, and the little particles that make up the solid are not allowed to move. They can vibrate a little bit, so there's a little bit of vibration, but they're not allowed to move. If you sit in a class somewhere for your chemistry, okay, and everybody's all lined up and everybody's in their seat, a solid and you sitting in your chemistry class are pretty much identical. Because if you're sitting in your seat, you're probably not allowed to move, right? So you don't leave your seat. But while you're sitting in your seat, you are allowed to like wiggle around a little bit. Your leg get tired, so you change position in your seat. So you are doing a little bit of vibrating, but you're not allowed to move. That is very, very organized, very low entropy. Now in a liquid, the little particles are able to move, right? That's what changes a solid into a liquid. Solids, the particles can't move, but in a liquid they can. Now they're not moving very fast and they don't move very far. That's why you can see here these particles have the shadows really close to them. It's showing that they're moving, but they're not moving fast. Okay, now if you're in a typical high school, you have a class, the bell rings and you have to change classes, and so in between classes everybody's in the hallway. You being in the hallway between classes is a good representation of a liquid because you are moving, but it's pretty slow moving through your hallways to get to your next class. Now, if you've been in both classes and in hallways, you know that in the hallway, because there is some movement, that there is going to be more disorder there. Now, the gas, this is when school is out and you're out in the field behind a school playing some sort of sport. Okay? In a gas, these particles are moving very quickly. That's what this trail of little shadows is showing, right? They're moving really fast. And if you're moving really, really fast, like we talked about in the very beginning, then you are going to have a lot of randomness or chaos that goes with you, right? If we go back to that very first one and we said, as you heat an object up, it moves faster, and faster movement goes with more randomness and more entropy. Well, that's basically what we're doing here as we go from solids to liquids to gases. Very little movement, some movement, and then lots of movement. So very little disorder, some disorder, maximum disorder. Low entropy, some entropy, maximum entropy. So if you're going to predict if a chemical reaction or a physical change is going to have more or less disorder, more or less entropy, looking at the states are going to help. Okay, so let's take a look at this first example. We've started off with iron solid. So if you've got iron solid, all of the little iron atoms are all lined up perfectly next to each other. They're allowed to vibrate a little bit, but they're not really allowed to move. That has got a lot of order. This would be low entropy. Now, in this chemical reaction here, it's not really a chemical reaction, it's a physical reaction. We've turned a solid into a liquid. You've melted it, right? So someone took the chunk of iron, applied enough heat to it that it started to melt. Well, the minute it starts to melt, you start to get some randomness, right? The little atoms are no longer packed together, and they're able to move. So let's put little arrows here showing that they're all able to move in random directions. So this would have a higher entropy. Oops, forgot my R. Entropy. Sorry about that. Right? You went from total order to less order. So if your disorganization is increasing, if your entropy is increasing, then your delta S is going to be positive. Because you started from this much disorder, this much entropy, and then it got higher. So if it's going to start here and increase, that's a positive change because you have more of it, right? So that'll be your positive. Now this does become a little bit more complex when you're talking about chemical reactions, right? If you're going from a solid to a liquid, a physical change, just melting, or perhaps you're going to boil something or you freeze it, right? Those are relatively easy to figure out because you're just going from one of these to another one. But if you're talking a chemical reaction, usually you have multiple phases, right? Solid, liquid, gas, that's a phase. So if I look at this one here, I'm starting off with an H2 that's a gas. Okay, so in the beginning I have some H2. Let's draw them as little blue dots. And they are gases, so they are moving quite randomly, and they are moving quite quickly, right? We had said gases move quickly, and the faster you move, the more chaos you have. So this would be high entropy. High entropy. Now if I look at my BR2 is a liquid. So if we draw this, the liquids are also able to move, but remember, liquids move much slower. So these would have much shorter arrows. So if I considered this to be high entropy, I would consider this to be sort of a average entropy, right? So let's call it just some entropy. Now, what are you going to turn them into? You're going to take this high entropy gas, you're going to take this sort of entropy liquid, and you're going to turn it into some gas. Well, if you've got a gas, and let's make these black, gases are quite disordered. They're moving quite quickly. Now, we should talk about the numbers. You had one H2. Okay, so let's talk about one box of H2. You had one BR2, so let's talk about one box of BR2. But you're making two HBRs. Okay, so you're making two products. So really, I should probably represent it as two boxes, right? Here's my first HBr box, and here's my second HBr box. They are both gases, so for both of these, I should represent them as totally random movements that are quite extreme. So this would be high entropy, and this would also be a high entropy. So now if we look at the entire situation, you went from something that had high entropy plus sort of an average entropy. Okay, so you had lots plus you had some. And what you're going to end up with is products where the first one is high entropy and the second one is high entropy. So you're going from high plus some to high and high, right? You're definitely increasing because this one is going from high to high. This one's going from average to high, right? So for this problem here, you are going from lower total entropy to higher total entropy. So for this problem here, again, I would say that my delta S change is positive because I am increasing the amount of entropy, right? You went from some to more. And if you're going to increase, that gives you a positive entropy. All right, and the last one. If you have more particles, then you will have more disorder. Okay, think of it like socks. Let's say that you only own one sock. Okay, you're not a sock person. So if you have one sock and you put it wherever you store your socks, how much disorder can you have if you've only got one sock, right? You open up your drawer and there's one sock. Not very disorganized. But let's say that you own 12 socks. And for the minute, let's assume all 12 of them are different. So when you pull out your drawer, you now have 12 random socks in that drawer. How many ways can they get all tangled up and twisted up in with themselves, right? You're going to have way more disorder over here simply because you have way more things. If we go back to the babysitting example, if you're only babysitting one little kid, okay, there's going to be some disorder because little kids are a little chaotic, but you've only got one. Now imagine if you have 12 that you're attempting to look after, right? That is definitely going to be way more chaotic. So the more you have of something, the more randomness, the more entropy you're going to have. So in a chemical reaction, if you end up with more product than reactant, then you're going to increase the entropy. Okay, and that's kind of what I've got written here. Let's say that you could magically turn this one reactant sock into 12 product socks, right? I have very few reactants, and I have many products, right? Very few reactants, more products. Few reactants, more products. You're going from low disorder, low entropy, so this would be low entropy, to potentially a lot of disorder. So this would be high entropy. And again, if you're going from low to high, that's a positive change. So your delta S is going to be positive. So in a chemical reaction, you often have to count how many reactants do I have versus how many products. If you have more products, more chaos. If you have less products, less chaos, right? So if we take a look at the examples here, I have a xenon octafluoride, and it's going to react to give me 1 xenon and 4 fluorides, well, fluorines. So over here, total, I have 1 reactant. Okay, there's just 1 xenon octafluoride. But if you look over here on the product side, I've got 1 xenon, but I've also got 4 fluorines, 4. So I have a total of 5. So you're going from 1 reactant to 5 products. Okay, 1 reactant doesn't have much entropy. 5 products have way more entropy. So you're going to go from low entropy to high entropy. So if you're going from low to high, you've just got way more entropy. So your delta S is going to be positive. Okay, if we do the same thing for this reaction, this one's pretty much the opposite. You have aluminums plus some sulfur turning into aluminum sulfide. Over here on the reactant side, you've got 2 aluminums. You've got 3 sulfurs, so you got a total of 5 particles as reactants. But on the product side, you've only got 1 aluminum sulfide. So you went from 5 things, pretty chaotic, high entropy, to 1 product. That's pretty organized, pretty low entropy. So you're going to go from high entropy to low. If you're going from high to low, that's a drop. If you're dropping, your delta S is going to be negative. Okay. Now, I put the last one in here just to give us some bigger numbers. So if you have some octane gasoline and you burn it, say, while you're driving around in your car, you're going to use up some oxygens and you're going to produce water and carbon dioxide. So if we do a count, to make this equation work, you needed 2 octanes and 25 oxygens. So you needed a total of 27 particles. Over here on the product side, you've got 18 waters and you've got 16 carbon dioxides. So 18 waters plus 16 carbon dioxides. And that gives you a total of what? 34 particles. Okay, so you're going to go from 27, which is a lot. There's a lot of disorder here, a lot of entropy. But your product side is even bigger. You're going to end up with 34, right? So you ended up with lots more. So lots of chaos, lots of entropy, but you're going to go even higher. So more disorder, more chaos, more entropy. If you're going to go up, that gives me a delta S that is positive. Okay? Now, I had said at the very beginning of this whole video that part of the reason why we want to talk about whether you have positive entropy changes or negative is because the entire universe is tending towards chaos. It really likes positive entropy changes. And so anything that does that just naturally occurs or tends to naturally occur. Which is why if you take some gasoline and you add some oxygen and you light it, it'll just spontaneously and naturally burn. Right? Part of the driving force behind that, part of the reason why it wants to happen is because it's going from 27 particles to 34, which is increasing the amount of chaos or disorder in the universe. Right? That is one of the reasons why this reaction just naturally happens. Now, if you do want to talk about why are chemical reactions spontaneous or why they're not spontaneous, I do have a second video that explicitly looks at what makes a chemical reaction spontaneous. So you may want to check that out if that's part of the topic that you're working on. All right, now I've done all 4 of these in isolation, right? So we talked about if you increase temperature, you get more disorder. If you increase the number of particles, you get more disorder. If you dissolve something, you get more disorder. If you go from solid to liquid to gas, you get more disorder. So we talked about all 4 of them individually. But often, you end up with a reaction and someone is asking you, is the change positive or negative in the enthalpy? And you've got more than one thing happening. Okay, so what happens then? Like if I look at this chemical reaction here, you've got 2 things on the go. You have solids versus gases, so you have to consider the solid liquid gas thing. But you're also going from 1 reactant to 2 products, so you also have to consider the number thing. Okay, and for a lot of chemical reactions, you are going to have to worry about rule number 4, right? Which said if you have more products than reactants, you're going to get more entropy. Okay, so if you got a chemical reaction, you're going to have to consider this. But the other thing that you're going to have to consider is whether they're solids, liquids, or gases, rule number 3, right? Those 2 rules tend to be linked together, right? If you see one, you're going to see both of them. Now, it is very rare that you'll ever see heating or cooling, temperature changes, with anything other than just heating and cooling, right? This rule here doesn't tend to come with any of the other ones. And if you do talk about the dissolving thing, same issue, right? Here, when I did this, I was very careful to choose an example that had 3 reactants and 3 products because I wanted it to be 3 and 3, right? This is another one that tends to get jumbled in with the rest. So if I had a chemical reaction, I would have to consider aqueous versus solid, but I'd also have to count how many reactants versus how many products. So this rule too tends to get thrown into the mix with other reactions. So let's take a look at what we've got here. If I was going to decide if my enthalpy change was positive or negative, the first thing that I like to do is count, because it's the easy one. Right? If I look at this, I have 1 calcium carbonate, I have 1 calcium oxide, and I have 1 carbon dioxide. So I got 2. So I'm going from 1 reactant to 2 products. And we said if you are going to increase the numbers, you're going to increase the chaos, you're going to increase the entropy. So just based on the numbers, I'm thinking my delta S is going to be positive, that it's going to increase, right? If you increase the number, you increase the amount of entropy change. But if you look at solids, liquids, and gases, this one is a solid. If you're a solid, you are very, very organized. Calcium oxide, also a solid. So this is also going to be very, very, very organized. And your carbon dioxide's a gas. We know that gases are very disorganized, right? The little particles are free to move wherever they want. So for this one here, you are going from a solid, very organized, to another solid plus a gas. So you're going from low entropy to low entropy plus high entropy, right? These two add together. So if you've got a low and a high, that makes you higher. So this is also saying that you're going to go from low entropy total to higher entropy total on the product side. So it's going to be an increase. So this is also saying that my delta S should be positive, right? Because you're going from just solids to solids and gases. And the gases is what gives you the boost, right? You're going from organized to organized plus some chaos, okay? So the numbers are telling me delta S is going to be positive. The solid liquid gas is telling me that the delta S is going to be positive. So together, I'm pretty sure that delta S is going to be positive. So for this one here, I would say overall, delta S is going to be positive. They agree with each other and they reinforce each other. Okay, let's try the next one. Again, I like to count first. So if we do the counting, this here is sucrose, a little bit of sugar. So if you react sugar with oxygen, you're going to get water and carbon dioxide. 1 sugar plus 12 oxygens gives me 13 total particles. 11 waters plus 12 carbon dioxides will give me 23. So you're going from 13 pieces to 23. Okay, if you increase the number, you're going to increase the chaos, you're going to increase your entropy. So your entropy is going to go from low to high. That's a positive change. So based on the numbers, my delta S is going to be positive. Now, let's talk states. I'm starting off with a solid. So I've got a solid right here, all nice and organized. And I've got a gas. Gases are moving quite quickly. Gases are quite chaotic. So I've got the ultimate in order and the ultimate in disorder. Okay, what do you got on the other side? You got a gas. Okay, that's the ultimate in disorder. And you got a second gas, right? Carbon dioxide is also gas. So you also have a second ultimate in disorder. So you're going to go from order and disorder, right, these two together, to just pure disorder. Okay, order and disorder to pure disorder, right? So this would be like low and high, plus this over here would be high plus high. So if you're going from moderate disorder, because that's kind of the average between the two, to extreme disorder, your entropy is going up. And so based on solid, liquid, and gas, I would also say that the delta S is going to be positive. They agree. And if they both agree, then you know that this overall reaction is going to have a positive entropy change. All right, let's talk about the next one. Now this one here is an aqueous, aqueous, aqueous solid. So you're back now to talking aqueuses versus solids. But again, it is a chemical reaction, so you do have numbers, and you're going to have to count. So if I have 2 sodium phosphates and 3 barium nitrates, 2 plus 3 gives me 5. And over here on the product side, I have 6 sodium nitrates and 1 barium phosphate. 6 plus 1 gives me 7. Now, that's not a big change, but you did go from 5 to 7. So you are going to have an increase in the disorder, an increase in entropy. So based on the numbers, I think that my delta S is going to be positive. Now, let's talk about the states. And maybe I should draw them as like little containers. So we'll draw a container for the 2 reactants, draw a container for the 2 products. Okay, my sodium phosphate is aqueous. If you're aqueous, that means the sodium phosphates and the waters are totally randomly mixed. Lots of disorder, right? Aqueous, always got lots of disorder, lots of entropy. If you look at the barium nitrate, it's also aqueous. So you've got barium nitrates that are completely mixed up with the water. So again, lots of disorder. So on this side you have 2 aqueuses, which mean you have very high amounts of entropy, very high amounts of disorder. If you look over here on the other side, sodium nitrate is aqueous. Aqueous, you're dissolved, lots of chaos. So here's my sodium nitrates, and here's the water that it's dissolved in, right? Totally mixed up. But the issue comes here with this last one. Your barium phosphate is a solid. And we know that when you make a solid, the solid is going to settle to the bottom of the container. So all of my barium phosphate is going to be here at the bottom of the container, kind of as a pile of lump, right? A pile of solid. And the water is going to be floating on top. That's pretty organized. This has very low entropy because it's not randomly mixed up, right? Your solid is all at the bottom, your water is all at the top. It's very sorted. So you're going from 2 things that are very chaotic, very high entropy, to products where one of them has lots of entropy, but one of them doesn't. So it's much lower. So you're going from high entropy to lower entropy, right? Because you're increasing the order. You're decreasing the disorder, so you're decreasing the entropy. So based on that, I would have to say that my delta S is negative. Well, now I got a problem because the 2 things that I looked at are giving me contradictory answers, right? Based on the numbers, it should be positive. Entropy should be going up. Based on aqueous versus solids, my entropy should be going down, negative, right? And I can't have both. So at this point, you're going to have to make a guess or admit that you really can't say what's happening. So if I look at this, I have to decide really which one is more important, the increase in number or the production of a solid. Well, you see how the numbers aren't very different? You went from like 5 to 7. Think of it in terms of your socks in your sock drawer. If you had 5 odd socks versus having 7 odd socks, does that really create a lot more disorder? Probably not. So I'd have to say that this is probably a small contribution. But going from a totally mixed, like the chemical and the water completely mixed up, to having them completely separated, this is a big change. So if I had to say, I'd have to say that this is a small positive, but I'd have to say that this is a big negative. Now that's just a guess, right? That's just me taking my best shot at it. So for this one here, I'd either say unknown, you couldn't really tell me what the overall is, or if I had to take my best guess, I would say this is probably going to have a negative delta S, right? That would be my prediction. Now, if this number change had been bigger, let's say it was 5 going to 17, then I would say that these two would be basically about the same size. So you really couldn't tell which one wins, which one dominates, whether the delta S will actually go up or whether the delta S will actually go down, or if the two of them cancel each other out and the delta S is nothing, is zero, right? So this is a lot harder. All right, let's try the last one. Again, it's a chemical reaction, so we should count numbers. You've got 1 carbon tetrachloride, 1. It's going to turn into 1 carbon plus 2 chlorines, so 3. And again, you go from a low number to a high. If you're going to increase the number, you're going to increase the disorder, you're going to increase the entropy. So based on that, I think my delta S would be positive. Now, if we take a look at states, solid, liquid, gas, my reactant is a liquid. Okay, so they can move, but they're not moving very much. So very little arrows on these. Now, if I look at my products, my first product is a solid. Solids are very organized. They don't move very much. They just kind of vibrate. My second product, though, is a gas. So a gas, total chaos, right? They move very quickly. They move very far. Now, again, this is kind of hard to decide what's going on because you've gone with something that's sort of midway disorder to a solid, which is low disorder, and a gas, which is high disorder, right? So you're going from like middle level of disorder to a low plus a high. Now, when we talked about this, if I pull that sheet back, here we go. We had said that solids have low entropy, liquids have higher, but gases are super high. See how there's like 2 less than signs here, right? The gas is like the clear winner. So for this here, when I look at these 3, I've got liquids, solids, and gases. The main thing I should focus on here is the gases. So it would be like the liquid would be here, the solid would be a little bit lower, and the gas would be like way up here. So if you've got a really low disorder and a really high disorder together, these two would be, they'd average out to be kind of high. So you're starting with a liquid, and when I add these two together, it's probably going to be higher. But again, it's a bit of a judgment call. So based on the states, I'm thinking that I'm going from medium disorder to a much higher disorder. Sort of a medium entropy to a higher entropy. So if I'm going up, that would be a positive. So based on the states, I would think that my delta S would be positive. But it is a bit of a judgment call. Now, if you've called both of them positive, they agree with each other. So I would say the overall entropy change for this reaction would be positive. The most difficult problems are the ones where you get opposing sort of forces. One says positive, one says negative. Or you have such a mixture of reactants and products that it's a little difficult to decide increase or decrease. I hope that you enjoyed the video and I hope that it helps. If you have any further questions on spontaneous versus not spontaneous, like I said a little earlier, please check out my other video that talks specifically about how to decide if a reaction is spontaneous. And once again, thank you for joining me here at Chemistry with Dr. Clark.